In this video, we're going to learn about curve sketching. So what is basically curve sketching is we have some function y equals f of x, right? Now, when we have this function y equals f of x, remember, we want to sketch this curve. This curve can be anything like a radical function, a square root function, a rational function, can be a cubic function or polynomial functions, right? So in order to sketch a curve of f of x, we need some important key features. So what are the key features? Right. So the key features that good, x and y intercepts, excellent. Some of the key features that we need are x-intercept. How do you find the x-intercept? You make y equal to 0. So we say f of x is equal to 0. How do we find the y-intercept?
X equal to 0.
Good. You say y is equal to f of 0. We're making x equal to 0. In other words, substituting 0 in the function. Then we already know about x-intercept, y-intercept. What about the way the function is positive, negative, right? And it's equal to 0. So let's observe the function itself, f of x. Now, when f of x is greater than 0, what does f of x greater than 0 means? It means the function, when is the function above the x-axis? Above the x-axis is a very important key feature in pre-calculus. So this means when is the function positive? F of x greater than 0 means when is the function positive? This here means positive. All right. Then what about f of x? We'll do equal to 0 as well. When it's equal to 0, it means we are looking for roots. Okay. So in other words, it's basically the x-intercepts. Okay. When in the function is f of x is less than 0, we're looking for negative values. So we're looking for when is the function below the x-axis, below the x-axis. Right. So these are some of the important key features that we have learned in pre-calculus. Now, let's look at the derivative f prime x, right? What does f prime x greater than 0 mean? What does the derivative represent? The derivative represents, yes, it means we are looking for when the graph is sloping upwards. Looking for when the graph is sloping upwards. So positive slope. Yeah, when the slope is positive or when the function is increasing, that's what it means. Is increasing. When is it increasing? When f prime x is equal to 0, we are looking for horizontal tangents. Okay. In other words, when the slope is 0, we're looking for basically turning points. Turning points. Or you're looking for horizontal tangents. When f prime x is less than 0, we're looking for when the slope is negative. The derivative, right? We're looking for when the slope is negative. So, looking for when it is decreasing. Right. So, f of x is just talking about the x-axis, right? From the x-axis, what's happening? Is it above or is it below, right? Or is it at 0? Or is it at the x-axis, hitting the x-axis? For the increase and the decrease, We're looking for when the function is basically, yeah, for increasing and decreasing. I can't really draw x-axis there for you. So, but that's what it is. Increase and decrease when the function is sloping up and sloping down, coming down. Then we have the third one, which is f double prime x, right? Greater than 0. I want to do f double prime x less than 0, and then f double prime x equal to 0. Right, so when we have the double derivative, when it is greater than 0, we are looking for these types of shapes, right? We're looking for concavity. So when is the graph doing this? Now, in the concavity, you can have increase and decrease, okay? So this is called concave up when it is positive. So what it is? Concave up. When this is a sad face, it is concave down. F double prime x less than 0 is concave down. So what is concave down? When the double derivative is less than 0. So you can have an increase and a decrease, concave down. And then f double prime x equal to 0 is what we call an inflection point. What is an inflection point? It's like mixing up the two concavity, where the concavity changes. So see, you can go from concave up to concave down, isn't? So this is something like an inflection point is just right there where the concavity is changing. See, it's concave up, then it changes to concave down. So that's what f double prime x equal to 0 gives you. It gives you the x value where the inflection point is. Inflection point. All right, guys, you understood all that so far?
Yeah.
Yep.
Right,
Yeah.
excellent.
Yeah.
Now, sometimes for so these are just some of the basic key features, which is f of x, f prime x. Besides the x and the y intercept, you got f of x, f prime x, and f double prime x. So you got to know the positives and the negatives. You need to know the increase and the decrease, the concave up and the concave down, and the inflection points. Okay, and apart from that, when you go on to rational functions, something like this. Note. So when you go into a rational function like y equals f of x over g of x, then we talk about asymptotes, right? So for the horizontal asymptotes, we say y is equal to limit as x approaches plus minus infinity of, say I put f of x over g of x, of f of x over g of x. So you need to solve this limit for a horizontal asymptote, right?
It's like
And then
domain. The finding
no,
there which
no,
is zero, making the zero, no?
no. If you're making g of x equal to 0, then you're looking for extraneous solution, which is undefined solution, which is called the vertical asymptote.
Oh, it's vertical. Yeah, 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 exactly.
Yeah, vertical asymptote will be when g of x, or basically when the denominator is equal to 0, right? When the denominator is equal to 0. In other words, when g of x is equal to 0, then you'll get vertical asymptotes. Okay. So we will look at some of these functions, and then they further go on to describing end behaviors and stuff. You don't need to go so much into details of that, but we can cover it in coming up lessons. But these are like some of the important key features. So let's start with the first problem. Right. So the first problem is, remember, this is a polynomial function, right? F of x is equal to x cubed minus 6x squared plus 9x. So we'll do exactly what we have done above, right? And go through a polynomial function, which is this. Now remember, when you're sketching this graph, it's an accurate sketch indicating all the important points. Remember in the pre-calculus course, you just have to sketch the rough sketch, right? You just have to sketch the graph, which is not like scale and stuff. Remember, I'm going to indicate all the important points so you know exactly what the graph looks like. Now, let's start with x-intercepts, right? So we're going to say the x-intercept is x cubed minus 6x squared plus 9x is equal to 0. Remember, from this, you need to solve for x. Remember, you have the equation solver on your calculator. Let me just show you that. For a polynomial function, the equation solver on your calculator is this, right? See, the calculator is very powerful. You can go mode, go to equation number 5, right? What equation are you solving? You're solving a cubic equation, A, B, C, D, right? So remember, this equation is in the form ax squared, ax cubed plus bx squared plus cx plus d, right? That's the equation. That's a form of the equation. So that's why I'm using this, right? So you can, the value of a is 1, mode equation 5, and you're selecting option number 4. So 1, -6, and 9. Right, so before I get the answer, I want to solve it myself, and d value is 0, right? So I'm not going to press equals. Let's solve this. So I've got x into, I can take out the highest common factor of x. Remember, you have methods of solving these types of equation using the rational roots theorem and other techniques like synthetic division and stuff. You just need to choose one value that gives you 0 other than 0, and then use synthetic to factorize and stuff. But in this case, it's very easy. You can just take out x as a common factor. You're left with the quadratic minus 6x plus 9 is equal to 0. This here looks like a perfect square. So you got x minus 3 into x minus 3 is equal to 0. So x is equal to 0, or x is equal to 3 with the multiplicity 2.
Yeah.
Multiplicity is 2. Whenever you have multiplicity 2, or whenever you have even multiplicity, the turning point is always on the x-axis. I will prove it to you just now, okay? That's from pre-calculus. Whenever you have even multiplicity, you will always have the graph will turn on the x-axis. It can turn up or it can turn downwards, okay? Now, anyways.
Yeah.
Right, so that's great. We know that. So we got the x-intercept, the y-intercept. Now let's check on the calculator if that's actually the answer, right? So there's one answer is 3 and another answer is 0. There is no third answer, right? Suppose you give you 3 roots. Because of multiplicity 2, there is no third answer because the x value of 3 is repeated. Let's find the y-intercept. Y-intercept is finding f of 0, right? F of 0 will give me 0, okay? Right, so great. We have the x-intercepts and we got the y-intercept. Now comes the critical points. Critical points are basically points where the derivative points, all right? The stationary points. So f prime x. Let's find the derivative. The derivative of this polynomial function here is, yeah, that's easy, power rule. Give me the answer, someone, anyone.
Can I say? Can I say?
Yeah.
3x squared.
3x squared
minus negative 12x1. This is it.
You don't need to say x to the power 1. You can just say minus 12x and then plus 9.
Exactly.
Plus
Yes.
9. Plus 9 as well. 1 times 9 is 9. X to the power 0. Leave out. Right.
Yes.
So we're going to set this equal to 0 for now. Now let's divide everything by 3. So we got x squared. We're solving an equation. Minus 4x plus 3 is equal to 0. So x minus 3. We're trying to factor this out. X minus 3 into x minus 1 is equal to 0 because it minus 3 minus 1 gives us minus 4.
Yes.
X is equal to 3 or x is equal to 1. What are these? These are critical values. So how will I get the y value of the turning points? These are the turning points or the vertex? don't call it vertex point because vertex points meets at a V, right? So I don't like calling it vertex points. I call it a turning point, right? So you just try to use turning point thing. So you're gonna say f of 3.
Yes, sir.
Yeah.
Turning point is when the graph goes up or down, right?
No, the turning point is when the graph turns. There, up, then
Okay.
down. It's same as the
Uh,
stationary point. Yeah, horizontal
Sir, how do
tangent.
we know exactly that these are the turning points? How do we know they're not some other critical point on the graph?
Uh, okay, how do we know that these are the turning points?
Yeah,
Very
like
good
I
question.
understand because it's a quadratic or
No,
yeah, it's a
because
quadratic, but
because of the nature of the function that's given at the moment, the function that is
mm,
given is a polynomial function. All
okay, so we
polynomial
can just
functions will have
assume,
a
right?
turning point. Yeah.
Always, yeah, okay.
Example, in a rational function, you will get critical values that are in the denominator, but they will not be turning points. They will be
They won't be turning
asymptotes.
points.
Yeah.
Okay. Okay, so we just assume it based on the nature of the graph, right? Or the
Yeah,
nature
yeah,
of the
because
function.
no, it's
Okay.
not because of that. It's because the all polynomial functions are always continuous. There's no breaking point.
Okay.
It's always a
Okay.
continuous function. You don't have any denominator, so that makes this function
Mm,
undefined. So it's always
okay.
continuous.
Wait, so that means that continuous graphs have no or sorry, the
No
what's it
vertical
called?
asymptotes.
No, sorry, the discontinuous graphs that have like a break in the graph, those are also those points are the critical points as well, right?
Yeah, like in the
Okay,
rational
okay,
function.
okay.
I will come to
Okay.
that. So
Okay.
remember, all polynomial functions
Mm-hmm.
are always continuous.
Okay.
Polynomial functions. Yes, that's a good question. But anyways, let's stick to the basics of sketching this function. Right, so now f of 3, if I substitute 3 inside this function here, obviously if I substitute 3 inside this function, it will give me 0 because remember x equals 3 was what? Was my x-intercept. So if I
Yes.
substitute 3 in the original function, I will get 0. And if you substitute 1, you will get an alternative turning point. So what is this? If you substitute 1, inside here, you'll get 1, 10, you'll get 4, right? Because 1 plus 9 is 10, 10 minus 6 is 4, right? So you'll get 4. Now, comparing these two, comparing this value with this value, right? If you compare these two values, look at the y values. Which one is the minimum? Which one is the maximum?
Oh,
Because 0 is the
minimum?
minimum.
Yeah.
And for minimum, let's go back up. I forgot to write it here. When will you have a minimum? You will have a minimum when the graph, see something like this. You'll have a minimum when the graph decreases and increases, right? When will you have a maximum? When the graph increases, then decreases, then you'll have a maximum there, right? Okay, so let's get back here into our problem. Right, so we have a minimum here and we got a maximum at 1 and 4. So the coordinates of the horizontal tangent here is 3 and 0. We say this is a local minimum at 3, 0, and local max at 1 and 4. Right. Now, let's observe the increase and the decrease. So let's say f prime x, the full factored form of the f prime x was, remember I threw the 3 away here. It should have been a 3 there. Right. So this is a full factored form with a 3. But remember, 3 dividing both sides by 3 just gives me 0. So 3 into x minus 3 into x minus 1. 3 into x minus 3 into x minus 1. That's what the derivative is. Now I want to try to solve greater than 0, or I want to try and solve less than 0. Let's see how we solve it. We just draw one single number line and solve this. So easy. So what are the critical points here? It's 1 and 3. See how easy it is with the graph, with the number line. You can solve both positive and negative. Now let's see. F prime x, basically this is what we're solving, right? Substitute any value after 3 inside this derivative function, like the number 4. If I substitute 4 inside here, I will just get positive answer, okay? Once this is positive, you can alternate the sign provided that this is linear. If it's not linear, you can't alternate the sign because sometimes It can be negative, negative, positive, positive. In this case, if you substitute a value between 1 and 3, like 2, 2 minus 3 is negative 1. 2 minus 1 is positive. So that gives me negative, multiplying everything out. If I substitute any value less than negative, less than 1, like 0, I'll get positive. So what does the positive, the negative, and the positive represent? This here represents the decrease, that represents the increase, and that represents the increase. Now I can already see the shape of the graph. It's like up, down, then up. Can you see? Just using the derivative. Now let's go and check. Let me look at the so far. Sometimes you can sketch the graph just by using few key features. Now I'm ready to sketch the graph because I got bulk of the key features. Remember my y-intercept was 0, right? My x-intercept was, what was my x-intercept? It was 0 and 3. It was 0 and 3, right? And we said at 3 there is a turning point. So what kind of turning point? Remember, the function is increasing on what interval? X is an element, is increasing on
0?
where?
Oh.
No, where's the function increasing? From negative infinity to 1.
Oh, yeah.
It's increasing from negative infinity to 1, union 3 to infinity. Okay? And where is the function decreasing? It's only decreasing between 1 and 3.
Yeah.
Decreasing on x is an element from 1 to 3. Good. Now, remember, 1 is also an important point. So we're going to put 1 here down. At the x value of 1, we have at x value 1 of 4. Which gives me a maximum. At 1 and 4, it gives me a maximum. So what does the maximum shape look like? Maximum shape looks like this. Can you see? Sad face.
Yeah.
Sad face is the maximum. And at 3, what's happening? At 3 and 0, we have a minimum. So خلاص. We are done. Let's sketch the graph. It's going through 0, all right? And then we're going to join it up here and up there. Lovely. We have a cubic function, accurate cubic function with all the important points, 1 and 4. How do you know you have an accurate graph? When you apply calculus and find the turning points and the inflection point. It looks like the inflection point is somewhere around here. Can you see? The inflection point is changing. And I think the inflection point is maybe at 2. Let's check. Let's find the inflection point. So what was f of x? What was f prime x?
Equals to
F
0?
prime x was, what was f prime x? The function, 3x squared minus 12x plus 9.
Oh, yeah. Yeah, so
3x squared minus 12x plus 9. Now, to find the inflection point, you need to make the double derivative equal to 0, okay? So what's the double derivative? 3 times 2 is 6x minus 12 is a derivative of constant is 0. So 6x minus 12 is equal to 0. Remember, I made the double derivative equal to 0. Why? Because I'm finding an inflection point here. And I can see the inflection point occurs at 2. But I want the y value as well. So let's put it here. What are we finding? In this point, we are finding the inflection point. So let me write this, IP. Right, so we're finding the inflection points, IPs, right, inflection points. So x is equal to 2. If x is equal to 2, I can put the value of 2 in the original function and find f of 2, which is, what's f of 2? Put 2 inside the original function. 2 cubed is 8. 6 times 4 is minus 24. 9 times 2 is 18. What's this answer here? 2. Correct? 26 minus 24. Yeah, the answer is 2 there. So 2 and 2. 2 and 2. So what's the inflection point? Inflection points at 2 and 2. So what does the inflection point represent? And inflection point represents where the concavity changes, isn't? So let's look at the concavity change then. We're going to see when the graph is concave up. Concave up. Now, how do you check for concave up or concave down?
Double derivative is greater than 0.
Right. So we just find double derivative. We can factor this out because this is the double derivative. What is the original double derivative? 6 into x minus 2. You have to factor out everything. Now we draw a number line. And what's the important point in this number line here? The value, the number 2. So substitute any number after 2, like 10. 10 minus 2 is 8. 8 times 6 is positive. And less than 2 is negative. So what does the negative represent? The graph is going down. And what does the positive represent? The graph is going up. So where is the concavity changing? It's changing at 2. So that's where the inflection point is. So you can write concave up on concave up on x is an element. When is it concave up? From 2 to infinity. And when it is concave down?
From infinity to negative infinity.
Negative infinity to 2. Good. Right, guys. Hope this is making sense. Now look at the graph now. When is it concave up? Negative infinity to 2, right? Sorry, when is it concave down? From negative infinity to 2, and when it is concave up from 2 to infinity, right?
And
You have
also
any
one
questions?
question.
Yeah.
But you remember we find the multiplicity is even, it means that it's upper side of the x. If it will be odd, it means that it's downside of the x, yeah? If it will be 1 or 3.
When the multiplicity is odd, it means that it will just intersect the x-axis. It's going to be something like this because I'm looking at the function x cubed. So x cubed, 0 is a multiplicity, so it just crosses the x-axis. You can't, upside and downside depends on the negative and the positive of the graph. Example, if I change this function with a negative in the front, then you're going to have downside. In other words, the turning point won't be upwards, it's going to be downwards if I change this. But that's not the way to learn it. Multiplicity even, then the turning point is on the x-axis, and multiplicity odd, it just crosses the x-axis. That's it.
Okay, thank you.
Yeah, because that's pre-calculus. Yeah. So remember, when you apply pre-calculus knowledge, you can get the shape of the graph and the positive when the graph is above the x-axis, when the graph is below the x-axis. That's all we can do. But when you apply derivatives, you get a more accurate graph because you get the turning points and you get the inflection points. Why we need all this? Because sometimes you want to find the length of the curve. You want to find the length of the curve from 1 to 2, or from 2 to 3, or from 3 to 5. Then we can actually find it if the graph is sketched accurately. With pre-calculus, you can't sketch the graph accurately because in pre-calculus, all you have is key features, x-intercept, y-intercept, and when the graph is positive and negative. That's it. You don't do first derivative and second derivative. Right? First derivative and second derivative is for purely calculus course. Right, guys? Right, so this is a nice example of a cubic function. I will put more cubic functions in your homework. If you browse through the file, you see that each lesson, the homework files are there. I just need to update homework 12, which is on maximization, and homework 13. By end of this week, it should be updated. Anyways, let's move on to the second question. Second question, we're looking at a little bit more challenging question, which is a rational function. Okay. So let's observe a rational function. So second question is, we want to go and sketch the graph of this. Remember, by the way, if you don't know how to sketch any graphs, you need to take a lot of points, maybe between the critical points and stuff. You need to take a lot of points and then sketch the graph, right? So sketching graphs should be a very simple process because you are allowed to use a calculator. You can substitute different values of X and get different Y input values. And then you can determine the shape of the graph, like how it's turning and stuff, right? If you don't know how to sketch any function, that's what you do, right? You take a lot of values in between some interval and start sketching the function. Right, so anyways, this is our second example, which is y equals, let's call it f of x, not y. F of x is equal to 2x squared over x squared minus 1. So what type of function is this? This is a rational function. Right. Now, since this is a rational function, we will be looking at horizontal and vertical asymptotes, key features. So let's start with the key features. X-intercept, you're going to make y equal to 0. If you're making y equal to 0, just make the numerator equal to 0, isn't? Because no use writing out the denominator as well, like this x squared minus 1 is equal to 0. So if you cross multiply, straight away, just the numerator is equal to 0, right? In other words, you just have x is equal to 0. In other words, x is equal to 0 is with multiplicity 2. Nice. Can you see? So I'm just going to write m equals 2 instead of writing the entire multiplicity part. So remember, m is equal to 2. In other words, what does multiplicity even mean? It means there's a turning point at 0, isn't? TP at x is equal to 0. It's either up or down. We can't say whether it's up or down because we have to check. What does this means? It means that there's a thing going like this, or it's either up or down. But we can't assume that it's up or down because we need to apply calculus on this, right? So let's check. Oh no, you can determine whether it's up and down by looking at when the graph is positive or negative. It's possible. What's y-intercept? Y-intercept making x 0. If you make x equal to 0, you're just getting 0 over what you're getting, just 0, right? You're getting 0 over negative 1, which is just 0, right? So now we got x-intercept 0 and we got a y-intercept 0. But now we have a rational function. So we need to find other key features. What's the next key feature? Let's go and find the vertical asymptotes. And let's go and find the horizontal asymptotes. Right, so vertical asymptote, remember the denominator needs to be 0. Horizontal asymptote, the formula limit as x approaches plus minus infinity of f of x. Right, so now let's substitute and solve. Denominator is equal to 0. You guys are there, come on. Let's solve this. X squared minus 1 equals 0. So x is equal to plus minus 1.
X minus 1, x plus 1. Yes. Yes, like this.
Good. Right, good. You just take the 1 over and square root it. This one here, y is equal to limit as x approaches plus minus infinity of x squared. It was 2x squared over x squared minus 1. We can see the denominator coefficient is the same as the numerator coefficient. You can just divide. So the answer is just horizontal asymptote is just 2 over 1. You need to watch the video on limits to infinity and limits to understand this. Okay?
It's 2 over negative 1.
Why is it negative 1? It's 2 over 1. No, the minus 1 doesn't matter. It's just the highest
the
degree over
coefficients, yeah, highest degree
Yeah.
coefficients.
Look at the highest degrees. 1 here, 2 over 1. You have to divide by the highest degree of the denominator. Right?
Yeah. In the other
Remember
ways,
the-
it will be incorrectly, yeah.
Yeah. Look at the, remember the rules that we did? Infinite limits. Look at this. What's the answer? Same denominator. Numerator degree equals denominator degree, 3 over 2. Okay? Then I gave you when the denominator degree is greater than numerator degree, then the answer is 0, always. And then when
Yeah.
the denominator degree is less than numerator degree, the answer can be positive infinity or negative infinity. Okay? So don't forget these rules. It's important here now in curve sketching. This is where you apply it for finding asymptotes. All right, guys. Okay, so we have vertical asymptotes. We have horizontal asymptotes. What's next? Let's apply pre-calculus knowledge before we apply calculus. Let's see if we can try and solve this using pre-calculus knowledge. Now I want to see when the graph is going up and down. Sorry, not up and down. When the graph is positive and when is the graph negative. And by the way, what is the domain of this function here? Domain is all x values except these, right?
Positive
So
and
what's the
negative one.
Yeah. The domain is all x values except this positive and negative one. Okay. So remember, you can determine the domain from here. Domain is x is an element of real numbers except x equal to plus minus 1. Except x not equal to plus minus 1, right? Actually, it's better to write it in interval notation. Domain is, let me use a number line, -1 here and 1 there, not including. So domain is everything on this number line except -1 and 1. Right, so that's your domain. So write -infinity to -1, union, -1 to 1, union, 1 to infinity. Right? Should be not except, but x not equal to. X is an element of real numbers, but x not equal to. All right. That's the domain. Now, anyways, let's move on to, we want to try and find when is f of x greater than 0 and when is f of x, when is f of x positive and when is f of x negative. When is it positive or when it is negative. That's what we're looking for. So what do? We draw a number line by factoring everything out. 2x squared over x plus 1 into x minus 1. Now, we have critical values, okay? Rizwan, you were asking me this question before, right?
Yeah. Yep.
Yeah, so these critical values, these are all critical values. Numbers on the numerator and denominator. Numbers on the denominator are -1 and 1. Number on the numerator is 0. These are all critical values. It's just that -1 and 1 is already used up because those are vertical asymptotes. So you only have turning points at those important at those points there. But now let's see. When is a graph? What are we checking for? We're checking when is a graph positive and negative. In other words, when is a graph above the x-axis? In other words, this is the x-axis here. Okay. So choose any value after 1. Like, don't waste your time substituting on the numerator because the numerator is always positive. Okay. So let's just substitute in the denominator. Substitute any value after 1, like the number 10.
Or 2, doesn't matter.
Positive. If I substitute any value between 0 and 1, like half plus 1 is positive, half minus 1 is negative. Positive times negative is negative. Any value between -1 and 0, negative half, positive, negative. Negative. You see, don't ever make the mistake of alternating the signs because see now, any value between -1 and 0, substitute on the numerator is positive. Substituting the denominator, you're going to get -half plus 1 is positive times negative is negative. So you see now you're getting plus, minus, minus. Any value less than -1, like -10, negative, that's positive. So you see, it's not always alternating sign. It will only be alternating sign if everything is factored into linear factors. You see, x squared is not linear. You see, x plus 1, x minus 1 is linear, but x squared is non-linear. As a result, you can't alternate the signs. All right, so anyways, when is a graph positive? So f of x is positive if f of x is positive when x is an element from -infinity to -1 union 1 to infinity, right? And it is negative when it is negative 1 to 0, 0 to 1.
Mr. Mazelli,
Yes.
I have a quick question. So today I got an email for the math business project. Is that our project for this year?
We'll talk about this at the end.
Okay.
Right, let's continue here. Let's continue with this course, AP calculus. Right, let's see. Now, I think we can sketch the graph with only pre-calculus knowledge. All right. So what we're going to do is we're going to draw the X and the Y axis. All right. So we're going to put vertical asymptotes here. Usually when we draw
So
asymptotes,
sorry, I'm cutting, but before you continue, for f of x is negative, can't we just say x is an element of -1 to 1?
you can't, because 0 is a
Why?
critical value.
Oh, 0. Okay, it can't be 0, right?
Yeah,
Yeah,
it
okay.
can't, it
0 is
can't be
okay,
0.
okay.
Yeah.
Yep.
Because we're looking for positive and negative.
Okay,
Yeah, so
specifically, not just 0.
yeah,
We can't include it. Okay.
yeah, you can't include that. It's basically the correct term is strictly increasing and strictly decreasing. Right? It should be strictly increasing and strictly decreasing. But we're not looking for increase and decrease. This is just positive and negative because this is like my x-axis. I didn't find any increase and decrease because I think we can use pre-calculus knowledge to sketch this function. What was the horizontal asymptote, by the way? The horizontal asymptote was 2, okay? So we need to draw the horizontal asymptote as well because this is x equals to 1. That's x equals to -1. The horizontal asymptote is here. Yeah, and by the way, guys, you'll never find these types of graphs in, in your normal math and stuff. It's only in calculus course. All right, so let's continue. Maybe in pre-calculus they can give you one, but it'd be very challenging for the guys. All right, so there's my horizontal asymptote, which is y is equal to 2. Let me just shift this a little bit lower down. All right, and let's move this as well. Try to make it as a little bit accurate as possible. That's everything moving there as well. Let's break up this line. Okay, great. Now, we're almost there in sketching this function. Now see what's happening at after 1 is positive. So we know 1 is here. -1 is. And by the way, remember we had a turning point at 0, 0. And remember what I drew here. I said the graph can either go up or the graph can go down. Now my question is, can the graph go up? See what happens when the graph goes up. It intersects the asymptote. It can't happen, right? So the graph can't go up. The graph can only go down. Okay? The graph, because we have a turning point at 0, 0 because of the multiplicity 2. You understand this centerpiece is symmetrical here.
Yeah.
Are we right? Good. Now, oh yeah, remember what I said? It is symmetrical. So now there's very important concept of symmetry from pre-calculus, which is called even and odd function. We need to check if this function is even or odd. Right. So now remember what's happening. So we got everything sorted from -1 to 0, -1 to 1. Isn't
Yeah, we did.
from -1 to 1, what is happening? The graph is just going.
Down, no?
Yeah, the graph is negative. The graph is
Negative, yeah.
Yes, yeah. Remember, this is positive and negative, right? Now, what's happening after 1? Can I go and draw a graph somewhere around here? It's impossible for me to draw a graph here because I don't have intercepts. So you can't go and draw a graph anywhere here. After 1, where's the graph? After 1, the graph is here. There's a graph here. After 1, this is where the graph is. It can only be there. It's positive. And before -1, I can't draw a graph here now because it's going to cut the x-intercept there. And I don't have x-intercepts there. I only have x-intercept as 0. So the next graph is here. Okay. So I only used pre-calculus knowledge to sketch this graph. I didn't even use calculus at all, right? So rational functions, you can use pre-calculus knowledge. You don't need to use derivatives and stuff to sketch a graph. Now, let's check this graph. And I said, let's check for even and odd function. And what does this represent? What is even and odd function in general graph setting? So if you're checking f of x, f of negative x, and is equal to the original function f of x, then the function is even. Function is even. What does this mean? Function even means is symmetrical. Symmetrical about? Anyone knows? Symmetrical about the
The
y
axis of
axis.
symmetry.
Yeah,
Y-axis. Oh,
it's
the
symmetrical
entire
about the y.
y-axis.
Entire y-axis.
Okay.
See, if I fold this graph
So
in
this
half, you
is,
can see
yeah,
this is symmetrical, but we're going to
it's
show it
symmetrical.
now. Let's look at this function and check if it was actually symmetrical. So I want to check if this function was symmetrical. So I'm going to say y is equal to f of x, right? And the function was 2x squared over x squared minus 1. I want to check if this function was symmetrical. So I'm going to check f of negative x, which is
Negative 2x squared.
2 times negative x all
Oh,
squared
yeah, exactly. Yeah.
divided by negative x squared minus 1. So what am I getting? I'm getting 2x squared over x squared minus 1. Guess what? This is the
So it's
original
symmetrical.
function.
It's
Yes, I
even.
just proved that f of negative x is equal to f of x, which is even. So it is symmetrical about the y-axis. So function is even. Now, what happens in an odd function scenario?
Oh, it will be, if you put negative, it will be outside negative. Like this?
Yes, yeah. In an odd function, if you say f of negative x, it will become negative f of x. For an example, I will give you an example of this. Let's check a linear function, simple linear function, right? Linear function. Or let's check a cubic function, linear or cubic function, right? Not all, certain types. Let me check a cubic function, which is y equals f of x, and which is equals to x cubed. So if I substitute f of negative x, you get negative x all cubed, which is negative x cubed, which is negative. What is x cubed? F of x. So I've got outside negative, okay? So now the function is odd. So what is this? This is an odd function. Now, if you're looking at the shape of this cubic function, if you observe the shape of this cubic function here, you can draw it on your graphing calculator on Desmos and check what does the shape of this cubic function looks like. So the shape of this cubic function is something like this, right? And now, what is this? Isn't this is an odd function?
Yeah.
We just proved that this function is odd. I'm looking at specifically this x cubed function. Now, this is a y-axis, this is the x-axis, right? And the odd function is basically symmetrical about the origin. See, this is the origin. This piece here will be symmetrical on the origin, and it will become like this. So basically, if you get a point like 1 and 1, right, it's going to be symmetrical on the origin. You'll get 1, negative 1 and 1. Are we good?
Yeah, and also another thing I was taking that lesson before. There was the third one, the neither also, no? When it's not
Radical.
equal to the neither, which is not equal to
Oh,
the
yeah,
that
yeah.
and that.
Yeah. So if the function is neither even nor odd, then what's going to happen is you won't have any symmetries. Odd function is symmetrical about the origin, symmetrical about the origin. In other words, if you have a graph in the first quadrant, it will be like kind of like reflected in the third quadrant. If you have a graph in the second quadrant, it will be reflected in the fourth quadrant. Are we good? That's basically symmetry on the origin. All right, guys. Now, if you're looking at this function here, remember the very first function that we sketched, x cubed minus 6x squared plus 9x. If you try to do even and odd here, you're not going to get anything because this clearly the shape of this graph is not symmetrical anywhere. If you fold the y-axis, not even, it's neither even nor odd. Okay. So it's just we'll do more example. I will put some homework exercises on this. All right. So even and odd function, we touch on that as well. All right, so great, guys. So now remember we have this function here. Let's go back and apply some calculus and see if calculus can help us determine some important points or whatever. Right. So let's see with this function here. We already got the function. We are done. All right. Now I want to apply some calculus on this. Sorry, we just deviated a little bit because it was important that how come the graph is symmetrical about the y-axis is because of even and odd function concept. It is part of curve sketching, even and odd function. So now let's apply some calculus on this and check where the function is increasing, decreasing, and stuff, right? Now, just by observing this function, remember, just by observing this function, you can see where the function is increasing, right? I can see that the function is increasing from -1 to 0. Can you check? And then it's also increasing from -infinity to -1 and -1 to 0. And the function is decreasing from 0 to 1 and from 1 to infinity. I can see just by looking at the graph. You have to read from left and go right. You read from left to right. Read the graph from this end. See, you're going up, right? And then what's happening here? You're still going up, and then you're going down, and then you're going down. Okay. So that's where the increase and the decrease. Now let's apply some calculus because we need to find derivatives, right? So f of x is equal to 2x squared over x squared minus 1. Now, what is f prime x? We have to apply the quotient rule here, okay? So if you differentiate the top, you get 4x, leave the bottom, subtract, differentiate the bottom, you get 2x, leave the top, and divided by x squared minus 1 all squared. Now you have to simplify. That's the thing about curve sketching. So you're getting 4x cubed minus 4x cubed. That cancels out, right? See? If you open this up, you get 4x cubed. And if you open this up, you get 4x cubed. Everything cancels out. So all you're left with is, okay, let's just do it. 4x cubed minus 4x minus 4x cubed divided by. Now for the bottom, you have to factor out the denominator. You have to say x minus 1 squared, x plus 1 squared, because it's part of your critical points. Now, let's simplify this. Just negative 4x over x minus 1 into x plus 1 squared. Are we good, guys? Now, from this, we can figure out what are the, from this, we can figure out what's the turning point, all right? If you make the numerator equal to 0, you get x is equal to 0, which is the turning point. Isn't? So remember, we said that as well before. So great. Now let's find where is the function increasing and decreasing. So there are three important points, still 0, -1, and 1. Now, each of these, let's check. We are not going to waste our time substituting in the denominator because the answer will always be positive because it's square and square. So substitute in the numerator only. So if you substitute in the numerator only, that's always linear. So let's check. Substitute x value of 10, you get negative there. Any value between 0 and 1/2, you get negative. Substitute any value between 0 and -1. positive, positive. And didn't I say that the function is increasing from negative infinity to negative 1 to 0, and then decreasing from 0 to 1, and 1 to infinity. So it conforms. This here, the calculus confirms our increase and decrease. Are we good? So this is increasing, increasing, decreasing, decreasing. So the calculus confirms that our graph is accurate. Next
Sir,
part.
can we do a double derivative to find like
Yeah,
inflection points and
we are,
concavity? Okay.
we are
What
going
about
to do that.
what about turning points for the other? So we have the turning point 0, 0, but what about the like the parts on top in the positive side of the graph?
Are there any turning points? Yeah, there are some points there.
Yeah.
No. But these are not turning points because this part of the just
Oh, it's
increasing.
just increasing and okay,
It's just
okay.
there is no turning points there.
There is, it's not
Sorry, I
turning. Okay.
drew it incorrect. It should be like
Mm.
this, all right?
Yeah, okay.
It's just increasing and decreasing. There is no turning
Okay.
points.
It's not
Turning
like
point,
sharp or anything, right?
yeah. Turning points
Okay.
is turning point you will get when there's an increase and a decrease in the function. When the function changes from increase to decrease.
Ah, okay.
What is a turning point? Turning point is when the function changes from increase to decrease, like
Like
this.
changes direction and
Yeah.
everything.
Like,
Okay.
yeah, like over here, you can see there's a turning point at 0 because the function is positive, then negative, then it
Mm-hmm.
drops. So
Yeah.
there's a turning point at 0. Yes. Now, anyways, what's the f prime x function? Remember that was a simplified form, but we need it in a better form. Minus 4x over x squared minus 1 all squared. We're finding the double derivative now. Right, so now we're finding the double derivative. Let's find the double derivative. F double prime x is equal to, sorry, let me not write it there. Let's write it here. Differentiating negative 4x on top, you get negative 4.
Negative
Leave the
4.
bottom. X squared minus 1 all squared. Subtract. Differentiating the bottom gives me, we
2x.
need to apply the chain rule.
Oh, the
2
chain rule. Okay.
into x squared
2x
minus
squared
1
minus 1 all
times the
squared.
derivative of the inside,
Oh, we
2x,
brought the, okay.
and then leave the minus 4x.
Mm-hmm. All over.
Remember, this was f prime g, g
Minus g
prime
prime
f.
f.
Yes, that's what it is.
Chain rule, yeah.
So, yeah, f prime g, g prime f.
This is the quotient rule, right?
Sorry, not chain rule. I say I'm applying the chain rule here in the denominator only. It's a
Yeah,
quotient
yeah.
rule. It's a
It's
quotient
quotient
rule
rule.
in total, yeah. You still need to square the denominator.
Square the
So you're
denominator.
going to
So
get x squared minus 1 to the
minus 1.
power 4.
It's 4. Yeah.
Yeah. Now you need to simplify. That's the thing about inflection point. You got to simplify. So we need to take out the highest common factor here. So we're going to take out minus 4 from the first part, and from the second part also minus 4, and take out x squared minus 1 to the power. So there's your that one. Right. That's
So
your
minus 4x squared as the highest common factor.
minus 4
Minus
into
4
x squared minus
into
1.
x squared minus 1.
Minus
For the
4
first part.
into for both.
For both, okay. Oh, there
Open
it is.
bracket.
Okay. Yeah.
So
Okay.
if I take this and if I divide by this, you'll get 1. No, sorry, not 1. You'll get x squared minus 1. And if I take all of this and divide it by minus 4 into x squared minus 1, I will get minus 4, that cancel out, minus 4x squared, right? Let's check it out. The minus 4 and the x squared minus 1 disappears. So you're left with minus 2 times 2x minus 4x times x minus 4x squared. That's correct. All over x cubed minus 1, sorry, x squared minus 1 to the power 4. X squared. Now, there was a reason why we simplified, all right? Is because of this. See, one of this and one of that can cancel out. So it becomes 3 in the denominator. And what are we left with on top? What's on the inside? So we left with x squared, we left with negative 4. What is this on top? We are getting minus 3x squared minus 1. And now I'm going to take a 4 inside here. So I will get 12x squared plus 4. Are we good? 12x squared plus 4. Yeah.
Yeah.
Divided by, factor this out as well. So that's going to become x plus 1 all cubed into x minus 1 all cubed. Yeah. Now, remember that numerator is always positive, so we can't really find any real critical values. We're not dealing with complex numbers at all, right? So we're only working with real numbers. Avoid complex numbers in AP calculus. Now, we got just -1 and 1. We only have two critical values, okay? -1 and 1. Substitute any value after 1,
Let's
like
take
10.
Mister, are
10.
you sure that's correct? X
Yeah,
plus 1 cubed, x minus 1 cubed.
yeah, because I factored the denominator out. That's correct.
Oh, okay.
It's
The
x
squared is
squared
taken.
minus 1
Okay, x
all
squared minus
cubed. Yeah,
difference of squares all cubed. Okay.
yeah,
Okay.
yeah, yeah. Right, so take any value after 1 and put like 10 inside. So it get positive, negative, positive. So what does this represent? This here represents that it is concave up for less than -1. It is concave down between -1 and 1. And it is concave up after 1. Let's check up. See, this is concave up. This is concave down. And this is still concave up. But remember, there's no
Oh,
this
yeah.
piece. Aha. Can you say this is concave up, but there's no this part? It's still, remember, concave up and concave down still has the increase and the decreases in there. So this is still part of concave up. This whole thing is concave down. So great. We used calculus to confirm everything that this graph is correct.
It's much longer that, yeah?
Yeah, yeah. Obviously, because when you apply calculus, you got to know all your different types of rules. You got to know your product rule. You need to know your chain rule. You need to know your quotient rule. All the different rules you got to know.
So in the exercise, they will ask us for the proving it by using the calculus or not?
No, no, they will ask you for inflection points. Are there inflection points in this graph? Now,
Oh, yeah,
now,
okay, okay.
now, in this case, there is no inflection point because I can't solve this equal to 0 because -1 and 1 are undefined. So no inflection points here. No inflection points because x cannot be equal to plus minus 1, right? No inflection points, but they are concave up on x is an element from -infinity to -1 union 1 to infinity, and concave down on x is an element from concave down on x is an element from -1 to 1. By the way, guys, look, these are all that I applied calculus to sketch this graph. Now, I just want to go on to Desmos and show you the different types of graphs that we are looking at in AP calculus, right? 1 second. uh, so we have our graphing calculator here. Now, remember, we'll also be looking at functions like this. F of x is equal to square root x squared x to the power 2, right, minus 4. What does this graph look like? Let me just change this capital X to a small x. Yeah. Look at this graph. See what it looks like. Now, why does the graph look like this? The graph looks like this is because you have a restricted domain here. X squared minus 4, first of all, must always be what? Must always be positive. X squared minus 4 must be greater than or equal to 0. Then you'll have nothing in between -2 and 2, no graphs in between here. You'll get a graph on either ends. So you'll also be looking at graphs like this. You also need to look at power functions. F of x is equal to maybe 2 times e to the power x minus, sorry, I just go up. X minus 2 should be on the power. Why is it going like that? Let's put in
So you have to do
brackets.
-2 plus x.
Uh, minus, no, put in
Oh,
brackets.
okay. Oh, brackets.
All right, so not really this. This is too easy because this is like just shifting the graph. But if you put x squared, now you're talking. See what happens.
Yeah.
if you say 2 times e to the power x squared minus 2 is a power function graph, okay? The graph is called a power function. Let's take the 2 out, right? And you can apply calculus and x-intercept and y-intercept. Now, remember what I told you at the beginning. If you don't know how to sketch graphs, you can substitute a set of points and join those points and get enough information, right? You can also get a graph of trig functions, like a mixed function graph. F of x is equal to x times sine x. What does a graph of x times sine x look like? Okay, this is a bit too difficult, but you can see this is like it's symmetrical. Can you see? See, all these graphs that I did is like kind of like symmetrical about the y-axis, isn't? Can you see? Look at the second graph, the power function graph. This one here, the blue graph, is symmetrical about the y-axis. Even this graph is symmetrical about the y-axis. And even this graph is symmetrical about the y-axis. Now, wait. What if I look at e to the power x squared graph? Oh, no. That's too much of. Let's take that out. Let's say mixture of x and a power function. X e to the power x. See what's happening in this. Let's zoom into this graph and check what's happening here. Look at this. Now, x times e to the power x has, look at this, it has an inflection point because this is like changing concavity from here, concave down, then concave up. It's decreasing, then increasing. Can you see? So these are some of the graphs. I'll put in the exercises that you can try out, okay? So I'll just put it here for you. These are some of the graphs that we'll be looking at. And you have to apply calculus knowledge. You can't really apply pre-calculus knowledge on these types of functions. Right, guys. So let me just end off the sessions, then we can take some questions. 1 second. Thank you, guys. And